Hi, part 6, a practical application. In this particular case, we are taking a real life system and trying to see how we can model it. Response is not being looked at all. Only the real life system is looked at, and you are given clues to essentially group the masses and model the system. Deriving the equations of motion is left to you. By now, it should be easy for you to do by drawing free body diagrams or by using the Lagrangian approach. The problem has been taken from Mechanical Vibration by S.S. Rao, 5th edition. Page reference is given. The problem is taken for purposes of education from the textbook. Fundamentally, we are looking at a motorcycle which involves, as we know, an engine, a transmission, two wheels, chassis, fuel tank, and a rider sitting on top of it. The weights of most of these independent components is given in the table here. The data has been taken from the web. No particular model has been taken. I've tried to average out the data so that a representative mass can be taken into consideration here. Now, one would be bound to ask what is the mass of the individual components and the stiffness and the dissipative coefficients of the individual components. Most of this data can be obtained by doing certain amount of search, Google search on the web. Some references are given at the end of this lecture to guide you in how to do it. What is a first level crude approximation for a motorcycle? Well, the crudest of all approximation is to take the entire collection of mass as a single entity and the stiffness as a single entity and the dissipative forces as a single entity. So you have a standard spring mass and damper system. So if you lump all the masses together, it works out to about 300 kilos. So M equivalent G is equal to 300. It's easy to combine all the stiffness and find out an equivalent value for them. Similarly, in the case of the dissipative forces. As far as the stiffness is concerned, it's very easy. If you have a motorcycle and you have an access to the bike, all you need to do is probably to put some method of measuring on the cycle and load the motorcycle where the rider would sit with standard known weights. Look at it and see for 20 kilos, how much does it compress? For 40 kilos, how much does it compress, and all that. And you will get some rough idea of what the equivalent stiffness for the entire assembly is. So this particular first level crude approximation is not at all difficult. You can also say that as a first level approximation, the damping is 0. And if you say the damping is 0, you're back to the sample case that was done in part 5, where the free oscillation is very easy to determine. The running of the engine is a cyclic load. How it affects the system is something that you need to do some research into finding. But when the motorcycle is running on the road and it hits a pothole, goes down and comes up, that would be equal to an impact load. So the running of the engine can be modeled as a sinusoidal waveform, whereas the road surface can be modeled as an impact load. The response for the two individual loads can be easily determined independently and plotted against time and summed up to get the total response, because we have the superposition principle working in our favor. If the dissipation is non-zero, again refer back to the textbook Mechanical Vibration by S.S. Rao. The complete solution involving sine, cos, and exponent is there, and it becomes a standard spring mass damper problem. At this point in time, with a single mass, it's a relatively easy problem to solve. Second level, improved accuracy. For purposes of improving the accuracy, we are dividing the system in two ways. We take the two wheels together, the shock absorbers become the stiffness and the tire. We take the rest of the vehicle and the rider separately. So if you look at the figure, you see MV plus MR, vehicle and rider, as one set of masses, and the other twice the wheel mass as another set of masses. So it becomes a two-body system, which is relatively easy to solve by drawing the free body diagram or even by writing the Lagrangian. The system does not take into consideration anything about the physical aspects of the vehicle. For instance, wheelbase doesn't come into question. After all, a motorcycle is a device largely deemed to be symmetric about the longitudinal axis. But you have to take into consideration when you're looking at the motorcycle, the wheelbase, which is a significant distance between the wheel centers. With the advent of the two-body problem, we also move into matrices M, K, and C, which were essentially variables, single variables. They now become matrix variables. Largely, very often, the matrices will be diagonal, making it easy for us to handle them. But if the M matrix is not diagonal, the system is deemed to be inertially coupled. And if the K matrix is not diagonal, it is deemed to be stiffness coupled. These non-diagonal elements can create a lot of problem in solving the equations. We may eventually have to find suitable numerical methods to use to find the response of the system. Third level, improved accuracy. You start identifying the masses individually. If you look at the figure now, you will see MV plus MR. You will also see the mass of the wheels, the tires represented separately. There is a gap between the two where you can define the wheelbase. This now becomes a 3-degree of freedom model, and the equations have three variables: moment of MV plus MR, moment of MW, and MW. You can divide the problem in half and solve it, or you can solve the problem totally. For all practical applications, you can even leave out the rider and look at the free response of the vehicle by just taking MV alone, setting MR equal to 0. Just make sure that suitably you assume the stiffness and the dissipation. It's by and large, I would have to say, the last step in modeling the motorcycle. You have something that is quite representative of the motorcycle, because if you think of the motorcycle in your mind's eye, what you see is a large horizontal mass which has got 2 points of contact with the ground, which is exactly what this model has. So as it goes, this model should be quite realistic. Final level, everything is grouped independently and the masses are being broken down as much as possible. In this case, the vehicle mass is now set separate from the rider. There is an independent stiffness for the rider and an independent dissipation for the rider. And you find that the total thing is a fourth order system because you have four masses. Now, given the equations of motion referred to as EOM and the free body diagram referred to as free body FBD, you find that the equations become 4 by 4 in this case, though there will be a large level of symmetry due to the two wheels. The wheelbase will definitely come into play, and this is probably the most accurate model. However, with all these conveniences, one still has to use numerical methods and a computer to solve this problem. Fundamentally, the wheelbase and the mass are isolated and they bring in more and more realism into the system. But one must actually solve the problem independently to see how much the movement of the body as a whole becomes more and more accurate from the first level to the fourth level. That can only be seen by actual attempt. I'm giving a few references here because I'm not solving this problem totally. At some point down the line, I will take a 2 by 2 or a 3 by 3 or a 4 by 4 system and I will solve it using computerized models and show you using simple software like Excel how to get the movement, the mode shapes, and the natural frequencies. There are some references here which at this point in time will clue you in on how we will attempt it later. The first amongst them is the design and analysis of a shock absorber. The next is, of course, general optimization of suspension and things like that. The third, this one particularly is worthy of study. It is a complete modeling of a motorcycle using MATLAB, and you should take a look at it and read it fully. Like we have modeled a motorcycle, it is possible to model an aircraft. I have given a rough and ready reference for that for you to take a look at. After all, an aircraft is nothing but a horizontal beam with discretely located weights, and that could serve as a first level approximation. We can even model cars. Cars have an enormous amount of simplicity. There are standard models existing in the last 50 years, which are called quarter car models or half car models. You can look into them by Googling for them on the internet.